Hello, Mr. Ryan, are you right?
Mm-hmm.
So we talk about that generate binary string without the consecutive zeros, right?
Yeah.
And then remember last time we found the Fibonacci thing, right? Remember, with the length 1, we want to generate binary string without consecutive zeros, right? For example, if it n equal 1, we have 0, we can have 1, right? If n equals 2, we have 0, 1,
1, 0.
1, 0, and 1, 1, right? So how many here? There's 2 here, right? And there's 3 here, right? So the next one is, let's write this, okay? So this is basically binary tree, right? And then 0, 1, the next one we could have 0, 1, 0, right? And 0, 1, 1. Here is 1, 0, 1. Can we put 0 here? No, right? Because they'll violate that conditions, right? And here would be 1, 1, 0, and 1, 1, 1. How many? 5, right? So we can keep going on, and this one is 8, right? Yes?
Yeah.
So, okay, so we talk about breadth search, depth search, and then for the breadth search, we actually talk about 2 solutions. So today, let's study why this is a Fibonacci number. You know, I'm more curious in why this is 8, and the next one is 13. Okay, this is a mathematical problem, okay? So, do you have any idea?
Right, let me think.
Yeah, because we look at it, oh, it's Fibonacci, but we need to study why it's a Fibonacci. Okay, so this is f, right? When given this f1 equals 2, f2 equals 3, f3 equals the 5. So fn equals to the previous 2 sums, right? n minus 1 plus fn minus 2. And then
You can have 0, 1.
Which one?
You can have 0, 1.
This one?
The one below.
Yeah, 0, 1. Yeah, that's if n equals 2, we have 0, 1, 1, 0, 1, 1. There are only 3 solutions without the consecutive 0 because we can't have 0, 0s. If the task is to count how many, then we can just solve this equation, right? Using the recursion with the minimization or the iterative dynamic programming, right? This is very trivial to solve it. Or even we can use the mathematics the equation. Actually, there's the mathematical equations to calculate the nth Fibonacci number, but this is out of the scope today, okay? Yeah. So if we want to count instead of listing that, we could just solve this equation, right? When n equals 4, then you can tell me straight away there are 8, right? There are 8, you know. Okay. So but why? Okay. I mean, look at this. It's not very straightforward, but let's look at this, the n equals 3. Let's just look at this n equals 3. Okay, n equals 3. So what are we doing when we put the n equals 3? We just take this, right? We can put 1 after each of them, right? Yes? Because putting 1 is always valid. The previous one. We can put 1. So which one is putting 1s? These, actually, putting 1, these, and then that, right? So n equals 3. Of course, we can take the n equals 2. How many n equals 2? We put a 1 there. So remember here. This is this, right? Because we're putting 1 here. Now putting zeros, it's a little tricky. So which one we can put a zeros?
2 of them.
Ones that end in 1.
Ending 1, right?
Yeah.
It's ending 1. If it ending 1, we can put a 0. Alright?
If
So
it's
ending 1.
If
So,
it's 0, then we can't. We have to put a 1.
so we can put it n equals when it ends 1, we can put a 0. So this one, why is it equals to this?
Because it
Can you see the relation between this, right? Obviously, this is putting 1, and this must be putting 0, right? This must be putting 0, all right? Yes? But how many of those we can put as zeros is coming from this, right? So this one, we can trace back a little bit, one step. So 0, 1, and 1 1. 0 1 and 1 1. These are the putting ones. These are the ending ones. So remember how we put the ending ones here. Right? So from n equals 1, we put the ones. Now it becomes ones. Then it can be used to plus zeros. Am I right? Does it make sense? It's one more step. One more step. Can you think of that? Okay, let me explain one more time. So fn minus 1. This is for the previous one. We can take as many results for the previous row n minus 1 because our task is to plus 1, right? If there are 3, we can just take these 1, 2, 3 plus 1. Then it becomes that, right? Now this is plus 0. But plus zeros is that we can't put the plus 0 if it ends 0. So we need to plus zeros only if it ends 1, right? Right? But where is this ends 1? Remember the previous one. We can take n minus 2, because n minus 2 plus 1 that would be n minus 1. Would be ending 1, and then we take the results to plus zeros. The number of the elements that end as 1 is the same as the previous row, which is n minus 2, right? Because n minus 2, we take n minus 2. What do we do after take n minus 2? If we plus 1, plus 1, that will become the n minus 2, right? This is n minus 2, f n minus 2. So if n minus 2, what happens if we move it to the n minus 1? Remember, we use this plus 1 as here, right? Remember here, this first term is to plus 1. Plus 1. So plus 1 that will become fn minus 1, right? Here, ends 1. Plus 1, what I mean is putting the 1 at the end. Okay? So that's about how we visually prove it, right? Does it make sense?
Yeah.
Eric, does it make sense now?
Yeah.
Okay, good. Any questions? Easy. So how do we solve this problem? We can define, right? Define fn. Then if n equal 1, return 2. If n equal 2, return 3. Otherwise, return this thing, put a cache. Okay. And obviously, we have better ways to solve it. We can start with the first two terms, right? A equals 2, B equals 3, for I in range, how many terms, right? And then AB equals A plus B, AB. So A, B, what's the next term? This is A plus B, right? So A will become B. Then B will become A plus B, right? And then the last term will return A, okay? Actually, this is n minus 2, right? Because we have already calculated the first two items. Any questions for this?
No, not really.
But do you understand, right? This is
Yeah.
how we get the Fibonacci number. Okay, that's it for today. Bye-bye.
Bye.
Bye-bye. Bye-bye.